Hi, my name is Adam. It wasn't 6 months, it was 6 weeks. This is why it's kind of impressive, as far as I'm concerned. I'm a consultant. Basically, I take companies that already have a pretty substantial understanding of what is their product. They also have a kind of a POC or a first run through over most of the features, but their problem is scaling. So basically, every talk we've seen so far was about how specifically to use Redis in a specific context, or what are the right features of Redis that we need, or the right setup. I'm not going to talk about it at all. I'm going to talk about architecture. And basically, this is the change that we were able to do from this small-scale system of. It basically supported up to 1,000 users, but effectively was used by 10 people. To support, I said Mllion because it's nice in the headline, but it was actually 20 million concurrent sessions to the system at every given moment. And this was done mostly by using the right architecture. To be very precise, the amount of code that had to be rewritten is very, very small. And I'll just get to it. Fair warning, I am using a lot of buzzwords. Big data microservice, stream processing, real-time, scalability, which we've heard all of them a lot today, and I had to add this as well. Redis is fast. If you haven't noticed, this is kind of a core idea. Right. So basically, this entire talk is about how we take big data, and big data is this huge buzzword that we all like to use. We use it to impress our clients. We use it to scare our competition. We use it to squeeze more money out of our investors. But it's usually incorrect. What we really want is fast data, especially if our system is a real-time system. We basically want to move from something like this. Let's take our huge database and cut it to tiny slices and do these tiny actions on each one of them, and then combine it into another database, and then use this whole data-centric approach. And move to something like this, which is just a funnel. Our data is, does this work? Yes. Okay. Our data is coming from the lower left corner and just flows through the system. And the further we go into the system, the less and less actions we need to take, and the system is becoming faster. So there is another type of stream processing most of us know of. It's this, the Formula T. Like every factory works like that. You have your conveyor belt that takes large pieces or materials that needs a lot of processing, and every time you make it a bit better and a bit more accurate to what you want to have in the end, until the end you have a finalized product that's made of all these different materials and all these different components. And some of them are very complex, or some of them are very simple. Yet every piece of this puzzle, every station is uniquely. Sorry, I kind of lost my words here. Is expert in a very, very specific thing. It does only one thing. It does it best. If we have a problem, it's easy to find out. If the headlights doesn't work, we go to the headlight station and see what's up with that. Basically, that's it. Okay, so. In very high-level words, we want to minimize state dependency. Why is that? If we have this huge data center in the middle of our data store in the middle of our architecture, and everything is working around this data store, the state of it is very fragile. Every little change to it can break something. We never know who initiated the change in the state. But if every one of our tiny blocks just has a small incremental change of state that is being done from one side of it to the other, we can really target our efforts where it hurts. Okay, so I'll say, basically this is what I just said. General state is bad. It introduces a lot of side effects to the system, which is just another way of saying global state. And actually, it's very common to see this in proof of concept, because it's very easy to design. Okay, let's just start writing something. Let's get a product out there. Let's get some value out there so we can show investors, or we can show our clients, or we can show whoever. But then 2 months down the road, someone is asking for us for this kind of change or the other, and this is not what was easy for us to design or not. This is an undesign, doing a data-centric model. So now we want to really engineer a system to what it should be. Right. Okay, so I'll go even deeper. This whole conveyor belt approach is very nice when you just speak about it in general terms, and you show it on the board and say, yes, this is a very nice system, and look how clean it is, and these 3 parts are just the same as these tiny parts, but only these specialize, whatever. When you start doing this, you find that you have 2 very big problems. On real time, you have emergent relevancy and contextual completeness, which are 2 very high spoken ways of saying we don't know if we have the answer, but we only care if we have the answer now. So yeah, again, you need to know what exactly you need to know. You need to know exactly enough to answer any request from the client, but you don't know when you'll have the data. You can decide, okay, if I don't know the answer right now, I'll guess, I'll go and ask someone else, I'll do an assessment, but this is on your engineers' part. This is part of the job of your engineers to say how good is good enough. Right. So splitting critical sections. In order to handle all this uncertainty, all these, we don't know if we know when the answer is whatever, you need to really subdivide your entire system. And basically what we found out in our tiny firm, that after working with a lot of clients, these are the 3 major parts. Filters, splitters, and dehydrators. The dehydrator I'll get to last because it's kind of the least intuitive. But filters are just what they are. They take, all they know is how to do. If this is relevant for me right now, if it isn't, I throw it away. I just don't waste any more time for it. And the job of this filter is to save time for everyone else down the line. So you might have this is the gatekeeper of your system. You'll have several of these all around your system. Each of them is gatekeeping whatever is down the line from it. Right. Splitters, they do, these are basically if statements, yeah, or routing tables. I'm taking, this information should go here. This specific tuple should go to the client, or this should be stored there, and the third should be reprocessed or whatever. Okay, and dehydrator is all they know is this is relevant right now, but I know when it might be relevant. This is how we handle uncertainty in 2 levels. We don't know that this information is relevant right now, so we don't want to keep it in our system. We don't want to circulate around. We just want to put it aside for later, because maybe then we will need it. When, how, and what is later, and maybe we will need it, all these questions are, once again, is the responsibility of your engineers or your system architect to decide how you use it. What is a stale message? When do we not want to replay it? So basically, a Dehydrator will take information from one side and stream it upstream to the beginning of the road. Okay, so if as if the user had just re-entered it. So let's look at this architecture again. Yeah, we have, from our system, we have the gatekeeper. Something goes into the system. Whatever is relevant carries on. Whatever isn't, we don't care about it. Okay, and then we split it. If it's relevant right now, yeah, the splitter is deciding what's relevant and what's not. If it's relevant, okay, let's split it to whatever processes we have downstream for us. Great. If it's not relevant yet, but we think it might be relevant later, we'll just throw it back up. But this tiny dehydrator here will just say, we'll just take this information and delay it. It's basically a snooze button for streaming data. Okay, so this is was all very high level and without any context, and yeah, whatever. Let's carry on with that. Sure. So this is a project we did for a client of ours who had a POC. He sold it to two companies, Sección Amarilla and Medio Tempo. These are the sports channel and Yellow Pages of Mexico. So, and they gave him a small playground. It's the city of Tijuana, and his POC worked for effectively 10 people. Yeah, they used it with 10 users. This was friends and family. They thought the system might support up to 1,000 users. They haven't tried it. They did a bit of a load testing, but basically that's it. And the whole idea behind the system was geo-matching between questions and users. More easily pictured like that. Yeah, we have live questions, which have their polygons that they're on the map. Like, is there an open seat right now on the beach? I don't know. I can ask someone, or I can go and look. Or if some other active user is next to it, I can pop the question to him automatically. So this is what the system does. It takes questions a question stream, and crosses it with the active user stream, which are two streams of polygons basically. And the real problem here was not this. This worked fine with the system they had. The real problem is Tijuana is more than 1,000 users. It's kind of a huge city, and it has, with all its surroundings, tiny cities and villages and whatever, it's around 10 million people. And because it's a border city, you also have border crossers, which means you get to around 15 million people. And today they use it in, as I said, around 20 million, but sure, we'll get to that. They started off with something like that. This is a very common, like, POC prototype style design. Yeah, we'll have the users and we have our workers, and they'll just go to the database and do whatever. And sure, and then we have some problem with managing what actions need to be taken. So let's put a celery up on it, and sure, and it will just make everything right. But this problem, as I said, failed in around 1,000 users, mostly because the system mostly spent more time orchestrating between these workers than it was to actually do the calculation. Right. So this is the system we designed for them. You can see the similarity. We have a filter, and then a splitter, and then a dehydrator. It's a one-tier system, which meant it was pretty simple to build. We used an R tree here. Today, if we were to build it again, we'd use Redis, because it's basically an R tree, only in Redis. And our metadata was and our splitter and dehydrator were based on Storm, basically stream parse, which is Python implementation of Storm. And we used Redis all over. We used it for caching, we used it for metadata control, we used it for the dehydrator itself. And this entire system was built in Python because this is what they had, and I didn't want to break their code too much. So eventually we got, today we have around 20 million, over even 20 million concurrent active users. This wasn't updated because I just met the guy. He was here. And he told me now they're doing even larger queries on the system, and the biggest polygon they used was the entire area of the U.S., including Hawaii, this is actually North America, including Canada, including Hawaii and Alaska. Yeah, of course. I don't know about Puerto Rico though. I didn't ask. Yeah. So. This is basically a very generic kind of slide. Sorry, I'll turn to that again. Yeah, this is a very generic kind of slide. We just, we had this element that I told you, which is awesome, and then we had this other element, which I told you it's awesome, and then we had this other element, which you don't know that's awesome, but I told you, and you kind of believe me because I'm here with the microphone in my hand, and. So, but these are are very generic. What do we do in our daily life? How do we take this to our system, which I, of course, don't know anything of, and you know all about? So basically, soft decisions are, if they're fast enough, they're much better than hard decisions. We prefer to be kind of right, fast, than be 100% accurate, but waste a lot of time on it. Okay, so estimations are very good. Good enough is better than perfect, which means we need to know when something is irrelevant anymore. It's a business decision. It's not an engineering decision. It's okay. When does this client does not care anymore about the data? If we're a news site, we can cache every second or every minute. We don't need to cache at every millisecond, because even if a user wants our front page every millisecond, it doesn't matter. You can wait another second until the front page would update. And dehydration is way better than computation, and I'll be more accurate about that. We prefer calculating things as late as we can. If we can, let's just throw it on the side. Let's just wait for later. If it's really relevant, if it's really important, we'll see it again. We'll do it then. So as far as I'm concerned, it's the best HPC cheat of all times, because it's kind of anti-intuitive. You think of okay, HPC, high performance computing, is let's calculate everything as fast as we can. And the other say, no, let's not calculate it until later. Let's just put it aside. Whatever, let's do it later. And that's kind of interesting and gives you a pretty major performance boost in most systems I used it on. Okay, so basically this whole lecture has an article to it. It was published on GeoPython. On GeoPython, this is the name of a convention. You can find it. You can get the slides from the site, I guess. And we also have a blog, and we have this Dehydrator model. And I'm going to talk a bit about Dehydrator model. I don't have a slide for it. I actually thought Veer would be a bit more precise about it. Yeah, sure. And a Dehydrator, as I said, it's just a piece of code that takes your events to some store somewhere and returns it on the right time. You'd think it would be pretty straightforward, but doing it in a way that you can really achieve good performance with is not as intuitive. We tried several ways of implementing this. We eventually figured out what's the best, and now it's a Redis model. You can use it. I know our clients used it, and they got a 1,000-fold increase in the performance from using Python that's calling Redis remotely. And if you find it even a bit interesting, I suggest you go look at this site, because we do have a lot of documentation there. Cool. So thank you very much. Yeah.